In this video, we're going to take a look at another example of how we can examine a typical exercise such as this in the drawing and use a static analysis to gain a more deeper understanding into the biomechanics of this particular movement. And so recall that when we talk about human parts, particularly the extremities, those are designed as third-class levers. And the bottom line here with a third-class lever is that to move a load, greater muscle force is required that's proportional to that load. And with a static analysis, we're going to assume in this particular situation where a person is performing a standard exercise that one would see in a gym, and they're doing a single leg hamstring curl or knee flexion. Now, in this scenario, to subject this to a static analysis, imagine the person has moved the load and is holding the load at this position, so they're no longer moving. Now, this is going to be our static, and we're going to analyze this part of the person. So we isolate our system of interest, and the key steps here to start out our static analysis is that once we've identified our system of interest, we develop a model. And I've done that here where I drew a rigid segment to represent the lower leg and use this triangle to approximate the shape of the foot. So instead of performing a static analysis on the leg, we'll do a static analysis on the actual model. Now, we would then draw our free body diagram and establish our frame of reference, and we'll do that here on the next slide. So here we see our system of interest. We have our model. Now this model has a contact with the upper leg, and because of the fact that the leg is designed for rotation, we would put a fulcrum at the proximal part of the lower leg, and this fulcrum represents the knee joint, and that's the point where rotation occurs around. And so usually, as indicated in previous videos, we don't draw external contacts, but once again I draw a shadow or a silhouette of the point of rotation for the fulcrum to give us context. We have our standard frame of reference up in the top right hand corner, but now we have a bit of a problem because our model, which represents the lower leg in our exerciser, is neither horizontal or vertical. So what we need to do here is we need to take our standard coordinate system, and I'm going to rotate that clockwise so that the x-axis is aligned perfectly parallel with the lower leg. And if we do that, then we can no longer call this the x and y axis. X is always horizontal, y is always vertical. So we give it a new label, and we just call it x prime and y prime. And that just indicates a new coordinate system where we take our standard frame of reference and rotate it to the system that we're going to analyze. So what we're going to do is we're going to draw our free body diagram, and then the next step is to use vector resolution for all the vectors per our new frame of reference, and that new frame of reference is x prime and y prime. So the first vector we always draw is that represents the weight. As long as our system has mass, it has weight. And so I draw that at an estimate of where the center of mass is approximately located, and I draw the weight always directed downward. And I give that the label of the weight. Now that's the weight of the lower leg and the foot combined. Now we know that in the previous diagram there was an additional external contact, and that was the force coming from the machine, the pad that the person is pulling up against. And so that's providing a resistance, and I'm just going to label that F machine, and this one I'm drawing perfectly perpendicular to the lower leg. Now we know that to do this, that requires the action of the knee flexor muscles, or in this case the hamstring muscle group, and I'm going to draw that vector where that muscle, where that group of muscles approximately inserts onto the tibia and is going to pull along the line of those muscles. And I'm just going to give it a general label called knee flexors. I could have also labeled this hamstring to give it a more specific reference, but we'll just go with knee flexors in this case. Now, what we've done here is we've found all the external forces. We're going to add one more at the joint here shortly. So the next step is to resolve all of these vectors into components that are parallel and perpendicular to x prime, as well as parallel and perpendicular to y prime. So by focusing on, we'll go up to the first one here, F machine. We see that this one is directed perfectly perpendicular, which means that it is parallel to y prime. So we don't have to do anything, we can just leave it as such. But now we see the w vector is neither parallel or perpendicular to our frame of reference. So we need to take this vector and resolve it into y prime and x prime components. And so these will form a rectangle that aligns with our w, our overall force vector. So the y prime force vector is headed, our w y prime force vector is actually headed in the negative y prime direction, while the x prime vector for the weight is headed in the positive x prime direction. We do the same with our knee flexor force. We know that there's going to be a component that's perfectly parallel to the x prime axis, and we label that F for the knee flexors x prime. And there's going to be a component of this force vector that is perpendicular to the to our model, and we're just going to label that one KF y prime. We have one more force that is occurring right at the point of rotation at the fulcrum, and that's our reaction force. So I'm just going to call that Fj for joint, and that's the reaction force that takes place at the point of rotation. And this reaction force is coming from the interaction between the tibia and the femur. And this one will have two components as well. So we resolve this one into Fjy prime and to an Fjx prime. Now the Fjx prime would normally, I'd move this over a little bit so that the arrowhead is going right into the joint, but I moved it down this way just for clarity purposes so that we can see it. Now that we have our free body diagram set up, we're ready to move forward with our equations of equilibrium, and we start with the special case of Newton's second law, where acceleration is 0, and typically we would start with x, but since we've adopted a new coordinate system, we're now going to sum up all the forces in the x prime direction, and those forces will equal 0. So we move 0 to the left hand side. I'll start at the distal end and I'll work my way up to the joint, and I'm going to start accounting for all of the forces that are parallel to the x prime axis. So I see F machine, it's not x prime, I skip it. I skip w y prime, I skip w, but now I see w x prime. And this one, as drawn, is going in the positive direction. So I include it as wx prime. I continue to move further, and now I encounter an fkf x prime, and that's where we resolve the force of the knee flexor muscles. So that's going in the positive direction, and we know it's in the positive direction because that's dictated by the position and the anatomy of where the knee flexor muscle group is. So I add that as a positive kf x prime. Now the joint reaction force here, Fj, I don't know what the direction is. I know there is a reaction force, but I have to make a guess. So I'm just going to draw the Fj in this direction. I could have drawn it coming from another direction if I wish, but regardless of the direction, I have to resolve it into components parallel and perpendicular to x prime. So I find I have an fjx prime, and it's going in the negative direction. So I enter negative fjx prime. Now we start over with our y prime forces. So once again, we go back to the foot and we start working our way towards the joint, and we start knocking off all of our forces that are parallel to the y prime axis. And the first one I encounter is F machine. And then I will add that to my equation, and I continue to move, and I see another one, a wy prime. I'll add that to the equation, and now I have an fkf y prime, and then I'll have an fjy prime. And paying particular note to the directions as dictated by my coordinate system, I'm going to add all those in right here. So we start with a 0 on the left hand side, and we have a negative force of the machine because it's going in the negative direction. We have negative y prime because that's going in the negative direction. Then the flexor y prime component is going in the positive y prime direction, and the fjy prime is going in the negative direction because that aligns with my initial guess. Now we have a system with a point of rotation, so we actually do have a moment equation here. And so we follow Newton's second law, set the angular acceleration to 0, and we find all of those component forces. So once we've resolved, we work with the y primes and the x primes. We don't work with w, fkf, or fj. So we find all of those components. Now we see the one common feature of the x prime forces, so wx prime, fjx prime, and fkf, f of the force of the knee flexors, x prime component. All these run through the point of rotation. And recall from our earlier video, if we have a line of action through the point of rotation, the moment arm is 0. So we need to find our moments where the forces have non-zero moment arms. And if we take a look at the force of the machine, if we move at a right angle to the line of action of this force, which is at a right angle, perpendicular, we see that it has a physical separation from the point of rotation. And so the length from the arrowhead all the way along the length of the segment is the moment arm for F machine. The moment for wy prime also has a physical separation for the weight component of the leg, as does the knee flexor y prime component. Now notice that the moment arm gets shorter and shorter and shorter as we go from F machine, wy prime, and force of the knee flexors y prime. And so with a shorter moment arm, the ability to produce a moment of force is diminished. In other words, with a shorter moment arm of the knee flexors, the knee flexor muscle group must produce a much greater force to counteract the moments generated by these other two components. So the key concept here with moments is that with our moment equilibrium equation, we only include non-zero moments, and those are vectors with non-zero moment arms. So even though a force is present, such as these joint reaction forces, either the resultant one or the component ones, they're all heading into the joint. So the joint reaction force will not contribute to a moment of force. So this ends this video on setting up a static analysis for a system that is not perpendicular or parallel to the x-axis.